before? Yeah, Zach.
I had a question on 2.5 problem 3.
Hold on. 2.53. Zach. 3. Find the numbers at which this one is not continuous. Okay. So find the numbers at which this is not continuous. So number one, you look at the three formulas, you find they're all simple functions. They don't have domain issue. So they're continuous everywhere. The only thing that can go wrong will be at 0 and at 12. Okay? So our job is just to check these 2 points. To check these 2 points, usually we just check, because it's piecewise defined, we check the left, we check the right. So let's take the 0, we check the left, we check the right. Then let's take 12, we check the left, we check the right. Okay? So on the left, for 0, you should plug in 0 into this. That gives you 9. On the right, at 0, you should plug in 0 into this. That should give you 12. Are they the same? Then there's no limit. Not to mention we have a function value here. So this is not continuous. Okay. Now at 12, you should plug in left to 12 here, which give you 0. You should plug in 12 here on the right of 12, which also give you 0. Are they the same? Therefore, the limit x goes to 12, fx is 0. Now you just need to check f12, which means plugging 12 into the function, not the limit. Then you realize for 12 exactly, it's here. You should do 12 minus 12, which is 0. Are they the same? Therefore, continuous. So my answer will be 0 and 12 are the only ones can go wrong, and 0 is the one. So just type in 0. You should be fine.
Awesome, thank you.
Yep. Aaron.
2.5, number 2.
How would you remove the discontinuity of f? In other words, how would you define f4 in order to make this one continuous at 4? Okay. They have all kinds of ways of asking this, but basically you just need to figure out what happens here. Okay, so fx equals x squared minus 6x plus 8, x minus 4. How would you make it continuous? That means it's not continuous here yet. Well, let's just take a look. Limit x goes to 4. Okay, that is x minus 2, x minus 4, x minus 4. You have 0 over 0, so at 4, there is a hole. Okay. Other than that, we could cancel them. We have 4 minus 2, which is 2. So not only we have a 4, there's actually a 2 here. Okay. So far, it's not continuous because there is a hole here. It's empty. So how do you make it continuous? You just define f4 to be 2. Then you will be able to fill in the hole. Sounds good? So the answer should be 2. f4 equals 2. Then you're all set. Okay. Other questions from the homework? All right. 2.4 is over. Last time we stopped at you were once exactly 3 feet tall. And then we did basketball, and then we did all those kind of things. So basically, it's called intermediate value theorem. Okay, so very interesting theorem. Check it out later. Okay, it has a lot of interesting applications. We have one more thing to talk about, limit. That is limit at infinity. Then we're all set. Limit x goes to infinity. Okay. Try to recall what we did before. We have limit at 2, limit at 3, which are all fixed number. Okay. Even though your limit can be infinity, it's not you're going to infinity from the beginning for your x. Now what we want to do is we want to actually let our x goes to infinity and see what fx will become. That's the idea here. Looks fancy, but if I just write it down, seems like it's not hard to do. Do you know the answer for this question? Well, basically what I'm asking is when x goes to infinity, which means x become as big as you want, what is 1 over x? 1 over 1 million. Smaller than that, 1 over 1 trillion. Well, keep going. Can you see that eventually this is just like as small as you want, so it better be 0? So it's not hard. Common sense. Judging by the graph, what does it mean? Well, we all know the graph look like this. We all know this graph never ends because I literally just write down this, but actually you can just make it bigger and then this one goes. And make it longer, this one keep going, keep going, keep going. But you do know one thing. That is when you go all the way to the end of the axis there, which it never ends, by the way, this one should be as close to 0 as you want. So eventually, in the end, we cannot draw, but this one is 0. So this tells you nothing but horizontal asymptote of a function. Sounds good? Okay, so basically, this is easy. It's the same as we did before, just plugging a big number to see what the trend is. Second, it's basically the horizontal asymptote. What about this definition? Negative infinity. It's 1 over 1 billion with a negative. Can you see it's still 0? Yeah. And that corresponds to the horizontal asymptote to the left. Everything makes sense so far? Okay, that's what we know. And that's what we want for limit at infinity. Let me write it down. Infinity. The notation is given by this. Or negative infinity. It corresponds to the end behavior of a function of fx, let's just say. So this is number 1. For example, what's the end behavior of x squared? Okay, in the end, does this one go forever? Bigger and bigger than infinity. Okay, so a normal answer for things like this is going to be infinity or negative infinity. That's very common to see because, of course, you are going all the way down to infinity, right? Of course, sometimes we may have some fixed number. That's what we call a horizontal asymptote. So horizontal asymptote, we will use h dot a dot for short later, fx if or usually you should have infinity. But if you have a number which is 2, then it becomes your horizontal asymptote. Okay. Let's try to think about the concept a little bit. Question, can a function have 0 asymptote, a 0 horizontal asymptote? Use your button. Say yes. If you think it's possible, say no. If you think it will always have a asymptote, at least one. Anton, you said possible. Can you give me an example? A function with no asymptote, horizontal asymptote.
Well, the first example that came to my mind would just be like y equals x. I wouldn't think has a horizontal asymptote. Or it
Because
doesn't.
we know the graph, and certainly this one goes forever. Or you can say, hey, let's check fx is just x. What's this? Infinity. What's this? Negative infinity.
Mm-hmm.
Not number, so great. So the answer is yes, possible. Then, can fx have exactly one horizontal asymptote? Let's try this. Yes or no? One asymptote, horizontal. Justin, you said yes.
Yeah, I said yes. I'm not sure exactly what the function is, but when both there's like a vertical asymptote at 0, then there could be a horizontal asymptote at 0 as well. And then both lines are in a positive.
So basically, on the right, you have one asymptote. On the left, you have asymptote. It's possible that they are the same asymptote, right?
Yeah.
Example, if we think about it, actually, this one will work. You just need them to be the same. All right, so 1 is okay. 2? This time, not only say yes or no. I want you to think about a function that you know that does have 2 different horizontal asymptotes. Julia? You said yes?
Yeah. I don't forget exactly which one again. I'm sorry, but it's like the one that's like in school we call it like this sideways snake. Yeah, that one.
Sideways snake. It's the first time I heard about it. Okay, sideways snake. By the way, it's frustrating. I live on the bluff. And this year I find probably already 5 or 6 snake skins in my yard, which is super annoying. And then I thought, like, if I just close the door, then I Google online, they can climb inside. And then I say, what if I'm on the second floor? And then they say they can climb stairs. So now I'm screwed. Seems like snake can get you if they want, which is really bad. So the only solution I have is try to scare my wife. So if she's more scared than me, I'm fine. Okay, either way, sideways. Does anybody recall what this function is called? Or does this shape ring a bell?
Is that
Andrew?
like tangent inverse? Oh, sorry.
You are claiming this one is, let's just call arctangent. Some people are more familiar with that. Or some people are more familiar with tangent inverse, but they may mean the same thing. They all mean the inverse function of tangent. So what is the shape of tangent? I don't know, like a raisin snake? Okay. Now, if you know this is tangent, what about its inverse function? Now back and check what you know about college algebra. You draw a 45-degree. That's called inverse function, right? Then you take this graph and flip it. Okay, take this graph and flip it. Therefore, the original vertical asymptote, after you flip it, becomes the horizontal asymptote, which makes total sense. Okay, so this is the raised snake, and this is the side snake, and we agree it's arctangent. I think Anton sent this. Okay, Anton, do you remember these two numbers?
What? Which two number?
This asymptote here and this asymptote here. How high is it?
Oh, shoot. Pi?
Are you guessing?
No, I'm saying that definitely.
Think about this. We can go back to tangent, right? That originally come from these two. Do you recall where these two are for tangent?
Oh,
Then that will be
pi
where
over
these
two.
are. Pi over 2. Here we go. This is negative pi over 2. So it's settled. It's possible for we to have 2. It's called y equals arctangent. By the way, in the exam, feel free to use either. You can use tangent inverse. You can use arctangent. I can read both of them. Okay. Moreover, limit x goes to infinity. Arctangent x equals pi over 2. Limit x goes to negative infinity. Arctangent will be the left side of the sideways snake. It's actually the one on the bottom. So negative pi over 2. We will use this a lot. Make sure you know this. It's not technically reciting. If you could relate back to tangent, then everything is straightforward. Good, good. Can function have 3 horizontal asymptotes? Yes or no? Yes or no? Aaron, you said yes.
So based off of the tangent graph,
Mm-hmm.
it goes for infinity for the x values. So you just inverse that, it should continue with the y's.
Just keep going like that.
Yeah.
And maybe like that.
Yeah.
Clearly there are like 1, 2, and 3, and maybe a 4 if we want to keep going like that. Can everybody see the drawing? Seems like from the drawing there's no restrictions, right? We can have more than 3. Actually, we can have 4, 5, 6, 7 as long as we want. But now I want to ask you to think again. By drawing, it's no problem. But if I'm going to ask you this, if you have 2 horizontal asymptotes and you draw a graph like this, that's 2 horizontal asymptotes, right? Okay. What is the limit? X goes to infinity, fx. Is it this one? Or is it this one? Or you have more than one answer. But if you have more than one answer, that means to take the limit, you have two possible answers. That means the limit does not exist, right? Right? Can everybody see from here? Okay, so from this point of view, we need to say, hey, really, we only have two limits, one going to the left, one going to the right. And they both have to be a number. That gives you two numbers. If they're the same, you only have one asymptote. If they're not the same, you have two, but there's no way you can have three. Otherwise, you have to squeeze two answers into one limit. From the beginning, that means the limit does not exist. Good so far? Okay. Second way to think about it, if you draw something like that, is this still a function? Can this be a graph of some function with two things going to the side? You need to check the vertical line test. What do you see? You see 2 points. This one is not a function because you fail the vertical line test. So only one part of them can exist. You cannot both exist. Otherwise, you're not a function anymore. Make sense so far? So just be careful. For horizontal asymptote, we have at most two. Okay. That also means if I ask you to find all the horizontal asymptote of a given function, you just have to check this. You just need to check this. The answer may be infinity that does not exist. They're the same, they're not, whatever. Once you finish this, you're done. That's the only two possibilities. Sounds good? Right. Question, how many vertical asymptote can a function have? Horizontal, you can only have at most two. Oh, let me put it here. What about vertical asymptotes? Can you have two? Yeah. It's a function. Can you have three? Yeah. That's just looks all right. So actually for vertical asymptote, there's no restrictions. You don't need that thing to be a function. So it's actually working for any number of asymptotes. You can do it. Good. That's the first idea. Number three, I just want to write down the precise definition again for fun. The careful version. What do you mean by this is that now for any epsilon bigger than 0, there exists, before we call it delta, now we call it elm, such that if x is bigger than m, then when x is big enough, the function can be as close to L as we want. So that's the precise definition. Again, this is not covered in exam or anything. I just want to show you again. Okay. And you should gradually get comfortable of reading things like this. That's the mathematical way. Okay. Cool. Now we go to the fun part. Finding the limit at infinity. Well, whenever we have something like this, we always go with what we know. Simple functions. Okay, polynomial. We have x cubed plus 2x squared minus plus x minus 1, something like that. As x goes to infinity, what do you think will happen? Try to recall. They all doesn't matter. We only care about the first term because this one is way bigger than the other, right? From here you can see it's always infinity or negative infinity, never asymptote. Sounds good? Cool. Rational. We just did it. This is rational. And clearly, horizontal asymptote is possible. Okay, so this is a tricky one because when we have something not trivial, exponential, does this one have horizontal asymptote? Plug in 0, you got 1. E to the 0 is 1. It becomes bigger, it's increasing. It's never negative though. Do you recall the graph like this? Therefore, yes. Limit x goes to negative infinity, e to the x is 0. That is the second one we need to know. Trig. What is the limit at the infinity of sine and cosine? Infinity? Between 1 and negative 1, so not infinity, not negative infinity. Does it stop at a number? That means eventually this thing smooths out and they actually gradually become closer and closer and closer and never leave that number. Not really, this one constantly leave the number. And the amplitude is actually still the same all the time. It doesn't degenerate. Make sense so far? For this case, we are going to say limit x goes to infinity, sine x is not infinity, not a number. It does not exist due to oscillation. Later, maybe some people will call it periodic. Okay. We're not too interested in tangent, cotangent, secant, cosecant. So for this one, let's just know this. The other 4, we can do it. We just don't care. 3 more. Radical. Now you know, radical is nothing but the inverse function of a polynomial. Right? If you want a horizontal asymptote here, you just look for a vertical asymptote here. Does polynomial have vertical asymptote? It's always smooth. Not possible, therefore not possible. Okay. Log, you want horizontal asymptote. You just look at exponential and say, do you have vertical asymptote? We just did it. The answer is no. Actually, it's the other way around. I have a horizontal asymptote, so this one should have a vertical asymptote, which is true. Okay. Finally, trig inverse. You need to go to trig and ask, do you have any vertical asymptote here? Again, we know tangent has one. Therefore, y equals tangent inverse x does have a horizontal asymptote. Sounds good? Everything we had before, we only have 3 things. Number 1, rational. Okay. Number 2, exponential. Number 3, trig inverse. We had this before. Octan. That's it. Oh, no. That's all the fact we know before. Now I just want to add one more, which is also straightforward. I don't want to bother to draw the graph, but just give you some examples. Basically, this one says this is 0 and this is 0. Do you agree? X is huge, then x squared is huge. X is huge, then square root of x is huge. Cube root of x is huge. X to the fourth is huge. As long as this one is positive, you are fine. The reason we want to stay away from negative is because what if you have x to the negative 1, which give you limit x goes to infinity, 1 over x. You have fraction inside of fraction. That's when things get tricky. You technically don't know if x is on the numerator or the denominator. Okay, so that's why we require r equal bigger than 0. Sounds good? That's all the easy ones. Now let's check the harder ones, the rational. We only did this, but the rational is more complicated than that. What's this? How big is the top? How big is the bottom? What is the infinity over infinity? It's the same asking what is infinity minus infinity. We know this is wrong. We probably need to be careful when we say this, right? Okay. Not easy. What can we do? Well, this is what I'm going to do. I have infinity. I don't want infinity. I want 3 or 4. I want a number. Right? Let's get rid of the infinity by dividing an infinity. Then you got a number. Is it legit? Well, basically you are dividing by infinity, but really you are just dividing the same term on the top and the bottom. They should be still the same, right? But once you do that, something interesting happens. That's going to be x squared over x squared plus 1 over x squared. One. 3. Still okay? So originally this was trouble. But now by dividing, these two become trouble. We switched by dividing. Now you guys are the ones harder. But what are they? When x goes to infinity. We said, right? If you see a power, it's positive, 0. And it worked. It's not 1, it's 1/3. Does it make sense to everybody? So the key point is this term here. You divide it by x squared. Okay, that solved everything. Because after that, everything transferred to the simple fact we know. That is, anything on the bottom with x, it's 0. All right. That is great. Infinity over infinity. What should we do? we should divide by something, right? What should we divide? X cubed this time. Because last time it was x squared, because these are square. That's why I do that. Now I want to do x cubed. You follow? You can solve this. The answer is for fourth, fifth, which is easy. Still okay? That's a pretty neat method, but then of course you see a limitation. What if 1 is 3 and 1 is 4? I mean, everything we did before, they are the same power, then we're fine. What about it's a 3 and a 4? On the top, we should go by 3. On the bottom, we should go by 4. And of course, we cannot do that. They have to be the same. Which one do you think we should take? Say yes if you think it's the top. Say no if you think it's the bottom. Let's try to click the button. Yes if we do cube. No if we do fourth. It's 7 yes, 1 no so far. We have 8 against 3. We have 10 against 3. 10 against 4. Okay, 11. Oh, 12. 12 against the 4. Okay. Adam, Milk, how much money are you willing to bet it's a yes?
Nothing. I'm not sure
Oh.
either is right, to be honest, but I don't know for sure.
You don't know for sure? Okay,
Yeah,
who wants to
I
bet?
don't
People who said yes, who are willing to bet some money there? Just say it. Anton, how much?
100 bucks.
Okay, $100 on X cube. Now, people who said no, who are willing to take Anton's bet? Just say if the answer is yes, you give Anton 100, and if it's a X to the fourth, you get $100 from Anton.
I'll take
This
him.
is recorded, by the way. Okay. Nathan, do you want to take it?
I'll take Anton.
Okay. Do you want to add to it?
Mm-mm.
100? Okay. Let's see who's going to win. The only way to figure out is just, let's do it, right? So Anton, let's put it here. Anton's cube. Let's do it Anton's way. Okay, we're going to name it Anton's. Just to make sure that who wins. Okay. Four. 6 over x cubed. So far, so good. The top is great. The bottom is 5x plus 4 over x squared minus 4 over x to the cube. That's Anton's way, okay? Now let's try Nathan. Four x cubed minus 3x squared minus 6 divided by x fourth. Okay. 0, 0, 0, 0. Zero, zero, zero. What's the answer? 0 minus 0 minus 0. Sounds good? Okay. What's the answer here? Anton, 0. So both go to the right answer. I would say this is the draw. Both work. Okay. But I need to ask you a question. Which way is better in terms of computational clarity? Because we need to do things in a uniform way, right? Anton, can you see that if we go with your way, we just need to do a little bit more mind work. That is, I need to know the limit of this,
Yeah.
which is additional work. But for this one, what's done is done. Right? Or you can even think about your way is actually doing this one again, and then divide by x again, and then you receive the 0 over 5. Make sense here? Okay, I would say both way work. So sadly, we don't have a winner. But I would say in our class, I think this way is more uniform, kind of. Okay, simply because it's easier to compute. Okay, so good job, both guys. That means if we have two terms, go with the bigger one. Okay, let's go with this one. You always still work. It's just, it needs additional mind work, which we prefer to not do. Sounds good? This is a method called the leading term. Okay, so basically, you're dealing with limit x goes to infinity of fraction. And you know it's going to be infinity over infinity because there will be some term here, there will be some term here. Now the way to do it is quite simple. You just, number one, find the leading term. That means the biggest one. If the top has a big one, the bottom has a bigger one, go with the bigger one. Okay, as Nathan did. Then do the algebra. What's going to happen? Let's do this. You divide by the leading term. What's going to happen is the leading term is going to be divided by itself, right? So it's going to give you a constant. We love constant. Everything smaller than leading term is going to give you something like 1 over x to some power. Because it's the leading term. You have x to the 4th divided by 6. You have 2 more left. Okay, that's why I'm called the leading term. And all these terms actually eventually goes to 0. That's the beauty of doing leading terms. Number 3, just let all these goes to 0. Find the answer. That's it. Is the logic clear? Questions? Nick. Oh, misclick. Okay.
Yeah, I guess I'm just kind of confused on some of the algebra, like going from like the second step to the third step.
Hold
on
on.
the right.
On the right. Okay. Yeah. Nathan step from. You mean from here to here?
No, the next one.
From here to here.
Yeah.
Basically, what we did is we take all these and set it to be 0. And the reason is because any number divided by x to any power, as long as it's positive, they all goes to 0 because the bottom is basically infinity. You have 3, a fixed number divided by infinity. That's the reason. Okay. And if you're looking for support, it's actually the thing we wrote in the red box here. Yeah. Other questions? It's Friday. Do you guys want to take a break? Okay, let's stop here. Next Monday, we do more exercises. Okay, feel free to leave. I will be here for questions. Adam.
I just had I mean, it's not like a problem question, but in my 2.2 web work, there's like 5 questions that aren't visible.
Hold on. 2.2.
Yes.
You have 5 questions.
Well, like there's no problem number 1, 2, 4.
Oh. Don't worry about it.
Okay.
Yep. It should show that you got 100%. If you have 100%, then you're fine. Yeah.
Okay. I just wanted to make sure I wasn't missing anything. So.
It's just playing with the index.